All right, so I'm going to give you a brief little introduction to something in math that we call sigma notation. And I'll tell you what it is in a second. It's a way that we can do something that is going to come up in the future often. And it's just adding numbers, but it's adding numbers that have a pattern. So you might think of a situation where you're asked to add 1 plus 3 plus 5 plus 7 plus 9, and you're thinking, oh, well, that's not too bad. I can just do that in my head or use a calculator. But what if I said I wanted to go all the way up to 103? How would you add up all those numbers? Well, it would be difficult. It would be kind of tedious. Or another one would be 9 plus 28 plus 65 plus 126 plus 217 all the way up to 1001. It's not as easy to see the pattern on the second one, but I promise you there is a pattern. And so the tool that we have, the operation in math, is called sigma. Okay, this is a capital sigma in Greek. This is a lowercase sigma, this one. This has a different meaning when you get to statistics. That means standard deviation. We're not going to talk about it, but that is the lowercase sigma. So you do hear those sometimes in math, meaning two different things. This sigma that we're talking about here means summation. And what happens here is there's a counter. It's often a K. Sometimes it's an I or a J, but it's a letter. And that counter does a very specific, predictable thing. It counts all the way up from whatever number is on the bottom to whatever number is on the top. So if I say I want the sum as K goes from 0 to 5, I need some kind of an expression in here. So let's make that expression K plus 2, okay? Then what this operation is going to do is it's going to go through all the K values, the integer values, 0, 1, 2, 3, 4, 5. K always only stops at integer values, no matter what. There's no way to set it up so that K goes 0 to 0.5 to 1.5, or 0 to 0.5 to 1 to 1.5. But if you want a summation like that, you can divide K by 2 in your expression. Anyways, I'm digressing. So in this particular one, K is going to go from 0 to 5. It's going to evaluate K plus 2 at each stop along the way. So 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5, 4 plus 2 is 6, 5 plus 2 is 7. And then what it does at the end is it sums up all those numbers. So 2 plus 3 is 5, 5 plus 4 is 9, 9 plus 5 is 14, 14 plus 6 is 20, 20 plus 7 is 27. Okay, so this equals 27. And you can actually go to Desmos. And this is an operation that you can enter on Desmos. You can enter it on your calculator too. If I do sum, and Desmos they use n instead of k, but it shouldn't matter. N plus 2, I get 17. Oh, I must have done something wrong in my math. 2 plus 3 is 5, 5 plus 4 is 9, 9 plus 5 is 2 plus 3 is 5, 5 plus 4 is 9, 9 plus 5 is 14, 14 plus 6 is 20, 20 plus 7 is 27. What's going on with... Oh, I see. I need to have the parentheses in here. 27. Okay. So now we're on the same page. Okay, so that's what sigma does. It doesn't have to be a linear expression. So for example, I could have something like the sum as K goes from 3 to 6 of K squared minus 1. And if you're starting along with this, you're thinking K is going to go 3, 4, 5, 6. K squared minus 1 is going to be 8, 15, 24, 35, When you add those together, 8 plus 15 is 23. 23 plus 24 is 47. 47 plus 35 is 77 plus 5, so 82. I can check on Desmos to make sure I have that right. I type in SUM. N goes from 3 to 6. I need my parentheses. I want N squared minus 1, and I get 82. Boom, that's what's up. So now you may be wondering what the answers to these funds I started out with were. How do I write that in summation notation? That's a little bit of a trickier question. And actually, for any of these questions where you're given a set of numbers that you want to sum together and you're asked to write a sigma notation expression for that, there's infinitely many that you could pick. So let's say I go from k equals 0, and at 0 I want to do plus 1. Then what's the last one? Sorry, this thing is going up by 2, so I actually want it to be 2k plus 1, and I can plug in 0. 2 times 0 plus 1 is 1. And what's the last one that I want to add to? Well, it's going to be 2 times something is going to give me 102. 102 plus 1 is going to give me 103. So 2 times 51 is going to give me 102. And actually, if you think about it, if I wanted to start at k equals 1, I could have done 2k minus 1. And instead of going to 51, I would have gone to 52. And there's infinitely many that you could have done like that. This one, I think the trick that may take you some time to pick up on is that I was using one more than cubic numbers. And so k is going to go from 2 to 10. Pretty cool. All right, so just a couple more things, and this is going further than we necessarily are going to go today, but I think that it's just helpful to see that where we're going with this. So let's say I have a domain or a set of x numbers between 1 and 3. I'm just going to show you, this is a little bit of notation. I want to break this up into 5 equal subintervals. So 5 equal spaces. How big is each space going to be? Well, 3 minus 1 is equal to 2. Actually, you know what? Let's go with 4 equal subintervals. Okay, if I'm going to break it up into 4 equal stretches, 3 minus 1 is equal to 2. 2 divided by 4 is equal to 1/2. Okay, so each subinterval is going to equal 1/2. So I'm going to go 1 to 1.5 to 2 to 2.5. And those are my 4 equal subintervals. And a lot of times what we're going to see these notated as are x with a subscript. The subscript is a number below a value. So I'm going to call the first one x sub 0, or x naught. A lot of times they'll call that x naught, x1, x2, x3, and x4. And then what a lot of times we're going to be trying to do in the near future, and this bleeds into calculus very much, this is a very important topic in calculus, is what if we're trying to find, say we have a picture like this, and I want to know this area, and I want to know precisely what that area is on a curve. So I can't just calculate the area of a triangle. You could think, well, I could calculate the area of a trapezoid, and that would be close, but we eventually want to get exactly right with this. I want to calculate exactly what that area is, and I'm going to think of that area as A. How might I go about doing that? Okay, well, one way that I could go about doing that is I'm going to take this diagram, and I'm going to split up that region into 4 equal subintervals. And I'm just going to go, remember, this was x sub 0, this is x sub 1, this is x sub 2, x sub 3, and x sub 4. And for each of those intervals, I'm going to go to whatever point that function is at the left edge of that interval, and I'm going to draw a rectangle. And then I'm going to go to the second interval, and I'm going to go to whatever point that function is at the left edge of that interval, and I'm going to draw a rectangle. Then I'm going to go to the third section, and then go to whatever point that function is at the left edge of that interval, and I'm going to draw a rectangle. And I'm going to go to the fourth section, and I'm going to go to whatever point that function is at the left endpoint of that interval, and I'm going to calculate what the sum of those four rectangles are. And you might be able to look at that and say that this is going to be an under approximation. And it is. It's going to be an under approximation because clearly there's area here, here, and here, and here that where the rectangles are below the function itself. So you might say, well, what if I don't want an under approximation? Or what if I want a range of approximations? And in this case, because the function is increasing, if instead of going to the left edge of each section, I go to the right edge of each section, I'm going to go in my first section, I'm going to go to the right edge in, remember this was x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. So if you look at what I did, I went to x sub 0, x sub 1, x sub 2, x sub 3, and never went to x sub 4. In my right endpoint, I'm going to go first to x sub 1, then I'm going to go to x sub 2, then I'm going to go to x sub 3, and then I'm going to go to x sub 4. I'm never actually going to go to x sub 0. But what I'm doing with the right endpoint is I'm going to the right edge of where the function is, and I'm drawing a rectangle there. Okay? And if you think of what these things are going to equal, well, I can say that my left endpoint approximation is less than A is like the value I know to be true, is less than my right endpoint approximation. And if you think of what is the left endpoint approximation, well, those are just rectangles, right? So the rectangles are going to be the length times width, or you might think of, instead of length, you might think of height. And what's the height? The height is going to be f of whatever the x value is. So if I'm thinking of my left, in the left example, it's going to be f of x sub 0 times, what's the width of each one of those rectangles? Well, it's 1/2, plus f of x sub 1 times 1/2, plus f of x sub 2 times 1/2, plus f of x sub 3 times 1/2. And if you think of what's the right summation going to be, well, it's going to be close, but it didn't start at x sub 0, it started at x sub 1. So it's going to be f of x sub 1 times 1/2. And the thing that I think is important to recognize is that when we do these, so this is just going to be pattern. We're going to do this a lot. It's going to become a little bit habitual. Keep in mind that if you look at what these two approximations have in common, they both have f of x sub 1. They both have f of x sub 2. They both have f of x sub 3. What makes the left unique is that it has f of x sub 0. And what makes the right unique is it has f of x sub 4. And if you go back to the pictures, what does that exactly mean? Well, if I think of this as 1, 2, 3, 4, those are 4 different rectangles. Well, you might notice that this first rectangle on the second picture is the same as the second rectangle on the left picture. So this would be, actually, you know what? I should really instead of naming those 1, 2, 3, 4, I should really call those 0, 1, 2, and 3. And then this is going to be 1, 2, 3, and 4. That's a lot. That's a crash course in what these are called Riemann approximations. There's going to be more this year, more next year, but this is just an introduction, and if you're overwhelmed and confused, don't worry about it.